Okay, so in part one we talked about Rolle's theorem, and that sets us up now to talk about the mean value theorem. I'm not going to go through the formal proof of the mean value theorem, but Rolle's theorem is used in that. Alright, so here's our setup. Suppose we have a function that's continuous on the closed interval AB, and it's differentiable on the open interval AB. Then for some x values, we'll call it C, that is in the open interval from A to B, f prime of C is going to equal f of B minus f of A over B minus A. So if you go back to the opener from part one, you might realize that this represents the average rate of change of that function over the interval from A to B. And then this, f prime of C, obviously represents the instantaneous rate of change. i.e. the derivative. Okay, so what this is saying is that if our function is continuous and differentiable, there's some value within that interval between the endpoints where the instantaneous rate of change equals the average rate of change. And so that's probably the best way to remember the mean value theorem. Remember, think of mean as average. So the average rate of change equals the instantaneous rate of change. Now, just like in Rolle's theorem, you have to make sure the hypothesis is satisfied. So it has to be continuous on the closed interval. It has to be differentiable on the open interval. If that's not true, we can find some cases where that wouldn't happen. And then we're finding the C that is between A and B, so it's not including the endpoints. And by the way, just like in Rolle's theorem, this isn't saying that there's only one C value. This is just guaranteeing that at least one C value exists. There could be more than one. There could be more than one spot where the slope of the tangent line is going to equal the slope of that secant line connecting the endpoints of the interval. Okay, so let's just go ahead and try and apply this idea to some examples. Find the value or values of C guaranteed by the mean value theorem for this function. And let's do this without a calculator. Okay, so first of all, we need to find the average rate of change. So let's find that. So for this problem, we're going to be doing f of 3 minus f of 1 over 3 minus 1. So basically, remember, that's just slope. It's rise over run. Difference of the y values over difference of the x values. And then we want that to be equal to the derivative at some value c. So the derivative of this is going to be 6x. I'm going to plug in a c for x instead of x. You can leave it as x, it's up to you, plus 1. So that's the derivative at c. So now I just want to figure out when these are equal. So first of all, what is f of 3? That's 27, 20, 23 minus f of 1, which is going to be negative 3 over 2. So that gives me 13 is equal to 6c plus 1. And so now when we solve this, we're going to get c is equal to 2. So there's only one solution. And then double check, is 2 in this interval? Yes, it is. Is our function continuous on the closed interval? Yes, it's a parabola. Is it differentiable? Yes, because it's a parabola, it's a polynomial. And our c value comes in between 1 and 3. It might help to look at, let's do this really quickly, let's look at a graph of this. Let's take 3x squared plus x minus 7 And maybe I'll zoom in a little bit. Or maybe I'll just fix the window. So 1 to 3. So let's go -1 to 5, let's say. And the y values, I don't know, -6 to 6. Not as nice as I wanted. Let's go -10. And let's go to 4. Okay, so I'm just going to keep going here. Let's draw a segment. Let's see how I can do that. Second draw. Let's draw a line, number 2, from, let's do it from the home screen, it'll look nicer. Let's go from 1, comma, y1 of 1, and if this doesn't work, I'm going to abandon ship, and 3, comma, y1 of 3, and that hopefully will do it. Oh. Yeah, but you can't see it too well. So, and then if I want to draw the tangent line, which here 5, and we know it happens at 2, it turns out that'll have the same slope. If I had more time and was making a video, I would do that better for you. Alright, so let's keep going. Let's jump to another example. Prove that the sine of A minus the sine of B, the absolute value of sine of A minus sine of B, is less than or equal to the absolute value of A minus B. So how the heck does this even remotely deal with the mean value theorem? I have no idea. I'm just kidding. So what we need to do is figure out, let's say we have a function. What do you think our function should be? Probably sine of x, right? What do you think our interval should be? Oh, probably a to b. And we know the sine of x is continuous and differentiable everywhere. And so we need to find somewhere where the average rate of change equals the instantaneous rate of change. So what's the average rate of change? Well, that would be the sine of b minus the sine of a over b minus a. And that should equal the average, the instantaneous rate of change. Well, that would be f prime. Well, what is f prime? Derivative of sine is cosine. I'll use x, you could use c if you like. But wait a minute, I know the cosine is always less than or equal to 1, don't I? So right now, if I just focus on this value being less than or equal to that value, it's starting to look like what we need to prove. So sine of b minus sine of a over the absolute value of b minus a is less than or equal to 1. And now the absolute value of b minus a I know is a positive amount, assuming that a is less than b. And so when I multiply that over to the other side, it doesn't change the inequality. So I have sine of b minus sine of a, absolute value, is less than or equal to the absolute value of b minus a. And that's not quite exactly what we were trying to prove, but with absolute values, we know the absolute value of x minus y equals the absolute value of y minus x, so I can actually just switch the order of these and say sine of a minus sine of b. And same thing with the other absolute value, I could say a minus b. And Oops. Fine. That's exactly what we were trying to prove. So you have to be a little clever on these problems sometimes when you see mean value theorem and Rolle's theorem. And you have to work a little bit. Sometimes just writing down some stuff and seeing where it leads you will help you solve these. Alright, let's go to one more problem here. Now this is a little different idea, but a lot of times these are pretty common problems that you'll see in a textbook section dealing with mean value theorem and Rolle's theorem. It says, suppose that f of 2 is equal to 1 and the derivative is between -4 and +3 for every x value in the interval from -10 to 10. What are the restrictions on f of 6? Alright, so let's get a visual for what this is asking. F of 2, here's 2, and we're talking about f of 6, and f of 2 is equal to +1. Let's say that's right there. Okay. So, since we know that the derivative exists over this interval, that means it's continuous over this interval. And so let's think best case scenario, because best case thinking, we want to see how far up this thing can go. Best case scenario is that the derivative is actually always 3 between 2 and 6. So that's the most it could be at every point. And in that case, this is going to shoot way up here. And if that has a slope of 3, that means for every 1 unit we go to the right, we go 3 units up. So if we're going 4 units to the right, we must go 4 times 3, 12 units up. And if we were at 1 to begin with, now we know we'd wind up at 13. So we know that f of 6 has to be less than or equal to 13. That's the greatest value it could take on. Now, what about in the other case? What if it was decreasing instead of going up? Well, the most that it could go down for every 1 unit would be -4. Let's say the derivative was a constant -4 all the way through the interval from 2 to 6. That means that for every 1 unit we go over, we go down 4. Take it way down to here. So if we go 4 units to the right, and that has a slope of -4, that means we will go down a total of 16 units. And if we were at 1 to start with, that'll take us down to -15. And there's your answer. So you know that f of 6 has to be somewhere between -15 and +13. Alright? What are the restrictions on f of -5? Now that's still within that -10 to 10 interval, so we know that these values of f prime still hold. So let's go back here, and here's 2, and that has 1. And we know that f of 2 is equal to 1. But now we're going all the way backwards to -5. Okay, so now it kind of works in reverse. If we have a slope, like the greatest the derivative could be is 3, which means it would be going up as we go to the right. But then as we go to the left, it would actually be going down. So the lowest that this could go, if we moved 7 units to the left, the most that this could go down would be 7 times 3, 21 units down. So if we're at, let me show you a visual with this blue point. If we're here, maybe we go over 1, oops, we go over, where's my point? I'll create a new one. A bigger and better point. There it is. For every 1 we go over, we're going down 3. 1 down 3, 1 down 3, 1 down 3, 1 down 3, 1 down 3. So the most we could have gone down total is 21. And if we started at positive 1 and we went down 21 units, that would take us to negative 20. On the other hand, let's get rid of those. Not that. Okay, on the other hand, we could go, if with a negative 4 slope, to the left of 2 means it would be going up. So for this 7 units, we're going to the left. 4 times 7 is, we would have gone up 28 units. So what that means is, with the slope of negative 4, if we go 1 over, get out of here, 1 over, 4 up, 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 etc., not drawn to scale, then if we started at y value of 1 and we went up 28 units, that would take us to y equal 29. And so we know that f of negative 5 would have to be between negative 20 and positive 29. All right, I have one last problem for you, and it's one of my favorites. A car passes a police car at 12 p.m. traveling under the speed limit of 70. Speed limit 70, car goes by, the radar says less than 70. At 12:20, 24 miles down the road, the car passes another police car, and this time it's traveling again under 70 miles an hour, which is the speed limit. The second officer, being a good calculus student, pulls the car over and gives the driver a speeding ticket. Explain. Well, the second officer, the calculus student, realized that as the car is traveling, if we graphed the speed versus distance, that it's a continuous differentiable function over that entire time period from 12 to 12:20, which is a third of an hour. And so by the mean value theorem, he or she figured out that the average rate of change equals the instantaneous rate of change at least 1 point. And so if we figure out the average rate of change, so that would be 24 miles minus 0. Let's say 0 was the starting point, and then 24 was where it passed the second police car. And then the time difference is 20 minutes, which is a third of an hour. So there's your average rate of change. And that must equal the instantaneous rate of change at some value c between there. And so this equals 72 miles per hour. And so the officer told the driver, by the mean value theorem, somewhere over these last 24 miles you must have been going at least 72 miles an hour, or exactly 72 miles an hour. Therefore you were speeding and you get the ticket. Is anybody smiling? Probably. You don't have to admit it. All right, so here's the homework assignment. In section 1G, I'd like you to do these problems. I think for this week, this was a lot for the lesson to watch and go through, and then these problems will probably take you a while. So I think for now, I'm just going to say this is what's due on Friday, so you have all week to do it. I know you probably have a lot of other work. A few of you are missing some assignments, so please get those in. Even though they're marked as late, don't worry about that. They just need to get turned in so I can mark down that you've been engaged. If you have any questions, please email me, and I'll try and help clarify some stuff. Thanks, and hope you're doing well.